of the n terms that comprise this quantity Sn. And so if you followed the 3 steps in the activity, you found then that that summation can be more compactly written in what we call a closed form. With this formula. So in other words, without writing out the n different terms that you're adding together, you could just compute this single number here. So that was kind of a clever algebraic argument there. I just want to go ahead and relate this back to previous material. So back when we worked with Riemann sums, we would have been able to write this using summation notation, and so I just want to add that in here. This is equal to the sum from k equals 1 to n minus 1 of a times r to the k. And let me just comment here that as we're doing that, this first term is the same as a times r to the 0, since any number to the 0 power is 1. So what we have here is that Sn is this the sum of n different terms, and your book calls this a finite geometric series. So it turns out that a lot of different processes are modeled in this way, and so these turn out to be useful objects to study. Now, in fact, I did have one comment I wanted to make here about the value of r. So notice up here in the activity we're requiring that r is not 1, and the reason for that is because in this formula here we need r not to be equal to 1 in order for this denominator to be a finite number. So it's actually the case, though, that if r is 1, we can still sum up Sn. It becomes really easy in that case. Remark, if r equals 1, then Sn is just equal to a plus dot 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 plus a. How many of them are there? There's capital N of them. So that's just a brief comment here. So it turns out that very often we are interested in knowing something, not just about the sum of the first n terms of this form. Very often we're actually interested in knowing something about the sum, where we would take terms of this form, but we would never stop. We would never terminate the sum. And so in particular, we're looking at an infinite sum of the form a plus ar plus dot dot dot. Let me add a couple more terms here. Ar squared plus ar cubed plus, and we'll just leave the dot dot dots. That will indicate that it just continues forever. So if we were going to write that using summation notation, we'd write it as k equals, oops, I just realized I have a little write-out up here. when I wrote this summation notation for the finite geometric series up here, let me go ahead and put this in red because it's a correction. I needed to start my indexing at 0. Okay. So down here with the infinite geometric series, we're starting our sum at 0, and we're just not going to stop it. So the upper limit here is going to be infinity, and we're looking at terms of the form a times r to the k. So the question is, how should we think of evaluating an infinite sum? And so if I asked you to tell me what the what the infinite sum of this geometric series above here is, what you might do is try evaluating the first 10 terms. Or, rather than say evaluating, why don't I just be more precise? Just try adding them up. So add the first 10 terms, and then add up the first 100 terms, and then add up the first 1,000 terms. And the question is, are these numbers stabilizing? And if so, then we might say that that the infinite sum should be that level that those finite sums are approaching. So do these finite sums do they approach some limiting value? And if so, that would be a reasonable definition for an infinite sum. So we will define, so I'll write it sort of colloquially here. If so, then define the infinite sum to be this limit. All right, and so I want to do an example, but before I do that, I just want to point out that there's a similarity here. Okay, so this is just going to be a quick remark, is that in fact this is similar to the way we defined an improper integral. So I'll write this is analogous. And in particular, an improper integral with an infinite interval of integration. Right. And so if you'll recall, if we were going to integrate from, say, a to infinity of f of x dx, right, what did we do? Well, we graphed our function, right, and then we look from a to B, and we let B get larger and larger, and we see if those finite areas are approaching some limiting value as B gets larger and larger. And so that's analogous to what we want to be doing here with our infinite sum. So, okay, so let's think about this then. If we are looking at our problem from the preview activity, we might be interested in a sum of the form. Let's see. We had recall that our sum Qn was equal to 5 times 0.08 times 1 plus 0.08 plus 0.08 squared plus all the way up to 0.08 to the n minus 1, okay? And if we use our formula that we derived up here for the sum of a finite geometric series, right? So Qn is such a finite geometric series. We'll end up with, okay, and this calculation is in fact shown in your text, right? So, so I'm just going to record it here so that you'll see it. So this is going to be equal to, if I simplify it here, this is just going to be equal to 1 over 2.3 times 1 minus 0.08 to the nth power. Okay, and then let me just remark here, this is using the formula from the previous page. Okay, and so we might be interested in what would happen. So this is the level in your blood at just before you take the n plus first dose. So we might be interested in knowing what happens as you let time go on. So if we want to know the long-term level of the drug in the blood, at least before you take the next dose, this would be the limit as n goes to infinity of Q of n. Okay, and so it turns out in this particular case, this is going to be the limit as n goes to infinity. You'll see here 1 over 2.3 times 1 minus 0.08 to the n. Well, in particular, what's really convenient here is that as n goes to infinity, 0.08 to the n, right, 8 100ths times 8 100ths times 8 100ths, that's just getting smaller and smaller and smaller. So in the limit, we would have that the level of warfarin in the blood is just equal to 1 over 2.3, right? And so it's approximately 0.435. Okay, so we're going to talk a little bit more about making this kind of a limit computation, doing these limit computations for general geometric series. before we do that, maybe I'll just pause a minute and go to, let's see, I'm jumping ahead a little bit, but